So a black hole, I mean, the way that they're made in nature, which is a good place to start, the ones that we observe in the sky are by the collapse of certainly the smaller ones, the collapse of stars, very massive stars. So you've got a very, very massive star, let's say 30, 40 times the mass of the sun. Let's go really big, and there are plenty of those around in the universe. And they hold themselves up against the pull of their own gravity by burning nuclear fuel, which releases energy, which creates a pressure, which holds them up. So they're in equilibrium, right? They're trying to collapse, and they're hot, and everything's moving around. They hold up, but ultimately they'll run out of nuclear fuel because of a finite size, and so they stop doing that and they collapse. And for these very massive things, tens of times the mass of the sun, nothing can stop them collapsing. And so they get denser and denser and denser. They collapse, they collapse, they collapse. Now, for every object, if you think about the pull of gravity on the surface of the surface of the Earth, then we know you can build a rocket, you can escape. You have to go at some speed, whatever it is, 17,000 miles an hour. Can't remember exactly what it is, but you've got to go to get out. If you crush the Earth down and make it denser, then you get closer and closer to all this mass, and so the gravitational pull at the surface gets bigger, right? And so if you keep crushing it, you can imagine you get to a point where you'd have to travel at the speed of light to get off. And it's called the Schwarzschild radius of the Earth. And that's for the Earth, it's about, if I remember rightly, about 1.4 millimeters or something like that.
Wow.
I know what it is for the sun. For the sun, it's 3 kilometers. So if you squash the sun down into a ball that was 3 kilometers, then you'd have to, even light couldn't escape from the surface. And that collapse is what makes a black hole. So it's when something collapses and collapses and collapses, nothing can stop it, and it goes inside its Schwarzschild radius. So there's a region of space where you'd have to go faster.
So there's
than light
space
to get
inside
out.
that little dot,
You
that
can't get
3-point something dot.
In Einstein's theory, absolutely yes, right. So the space, and essentially the thing collapses out of existence, and so you've just got this kind of really heavily distorted space inside. And this singularity that we don't know about somewhere, which is in a very real sense the end of time actually in there. And so you get this complete distortion of space and time. So that's a black hole. So it's defined by this region, which we call the event horizon. Got this, everybody knows the word, which is basically the region of space where if you go in, you're fine according to general relativity. You'll be in there, but you can't get out. And more than that, you not only can you not get out, but you are going to the end of time.
No way.
And actually, for black holes that are quite big, even like the one at the center of the Milky Way galaxy, these things that are millions of times the mass of the sun, the end of time is minutes away from you, even in the biggest ones. So you can go in, but the time's going to end for you. You go into the singularity if you like, but it's better to say you go to the end of time. So that's
can you see everything that's ever happened in that part of space, like ever? Like if you go in, you could watch it all happen, and obviously you can't come back out. You
can't actually. Yeah, it's actually a misnomer that people often say it, but it's not right. In fact, but I know. I mean, people have said it. Loads of people say it, but it's wrong actually. When you look at actually because you're in there. One way to think about it, because you're in there for quite a short time before your time ends. You don't receive anything like
there's no epiphany,
the whole future of the universe. No. So that's kind of interesting. It's cool, right? It's a really fascinating idea. These completely collapsed stars, the supermassive black holes, billions of times the mass of the sun at the center of galaxies, all fascinating. But in the reason they're really interesting is because in the 1970s. Stephen Hawking noticed that they're not. People say black holes aren't completely black, right? So you might think black hole, nothing escapes. So that's it. If you go in, you're gone, and it just stays there forever because nothing gets out. He found that they do actually radiate. They have a temperature. They behave like anything else, and radiation comes off them. It's called Hawking radiation, and that ultimately makes them evaporate away in the very far future, billions of times the current age of the universe, right? These things last forever, almost, but not quite. It looks like they evaporate. And that caused absolute havoc in physics. And the reason it caused havoc is because people were worried about what happens when you throw something in. What happens to the information? So if I get this book, Stephen's textbook, and throw it into the black hole, does that information get destroyed? Or does it come back into the universe in the Hawking radiation eventually? Now, it's a fundamental part of all of science, I would say, physics certainly. Information isn't destroyed. Right. If you know everything about the universe at some point, some time, you know everything's moving around and everything that's in there, then you can predict what's going to happen in the future, and you could predict what had happened in the past. Information is not destroyed. But it looked to many people like black holes destroy information. Because the question was, when this thing's evaporated away, what's happened to all the stuff that went in? Right? Has it all...
And then you said time ends.
Yeah, in general relativity, it's the end of time in the middle. So there's something funny going on, basically, in black holes. And this argument went on for 50 years. But it's probably still going on, but it's pretty much been solved now, most people think. The answer, basically, is the information comes out in the Hawking radiation. But in order to do that, we've had to completely destroy, I would say, our notion of what space and time is.
You said earlier about a black hole being something like 4 times the sun, and it will collapse at some point, and it's like the equilibrium between the two. So I assume, like, at some point the sun will collapse.
Yeah, but it's not massive enough. So there's something that will stop that. And so gravity, it's squashing it down. There's a thing called which is we actually spoke about earlier, which is the fact that electrons don't like to be close to each other.
Yeah.
Do you remember I said that plays a role in making things solid?
Yeah.
So what happens when the sun collapses is that those electrons get pushed closer and closer together in the collapse, and they move around faster and faster, trying to avoid each other. And that makes a pressure which can hold it up. It's called electron degeneracy pressure. But that means that, so for anything less than 1.4 times the mass of the sun, it's called the Chandrasekhar limit. Then
Chandrasekhar limit.
Then that's after the physicist Chandrasekhar who worked it out. Then that pressure can hold it up. So it becomes what's called a white dwarf star. So a white dwarf star is held up by that. There's another one. So if you get a bit more mass, and it goes again, because it can't, the electrons, basically what happens is electrons would have to move faster than light to hold it, and they can't. So it collapses again. The protons turn into neutrons, and you get a neutron star. And that's held up by the same thing, but for neutrons. And they're like, stars the size of cities. Those things are more massive than the sun and 10 kilometers across or something like that, held up by the neutrons. But if you do more and more and more, if the neutrons can't hold it up, and that's when you go through the Schwarzschild radius. Gets so small that you go through the event horizon. The event horizon comes out, essentially.
But that's not happening to our sun.
So they burn hydrogen into helium, which is what the sun's doing now. It's called a main sequence star. When they run out of hydrogen, then their core is basically helium. So the thing starts to collapse. And then it heats up to the level where the helium can start to stick together to form carbon and oxygen. That's where the carbon and oxygen in the universe come from. And that regenerates the star for a while, and it gets bright and hot. And then it will run out of that. And then the big ones can collapse again, and they can build things all the way up to iron, in fact, in their cores. And in the process, they swell up to become red giant stars. So they become enormous in that phase of their life. The sun will probably engulf the Earth in that phase. It might not quite. That sometimes, because it loses some mass, the Earth drifts out a bit. But roughly speaking, it'll come out. It'll certainly engulf Mercury and Venus and come out to what it'll approach the orbit of the Earth in size. In that final phase of its life, before ultimately it'll collapse. And the sun's not that massive. So
when do you envisage that happening?
We know it's about I mean, it starts to change in a few billion years. Ultimately it's got about 5 billion years left or so, and then ultimately what
Few
happens is the
away.
the outer layers drift away, and it becomes a white dwarf and something called a planetary nebula.